let's take a look at stellar characteristics and evolution. And we're going to start out by thinking about the information that we can get by using the light from stars. And that's important to think about because light is pretty much all we get from stars. So we can look at a star's spectrum. So if we plot the intensity versus wavelength for a star's light, we get something that looks roughly like a black body. Not exactly, but roughly. If it's roughly a black body, then we can estimate the wavelength of maximum emission for the star. And if we know the wavelength of maximum emission, we can get the temperature of the star using Wien's law. So there we go. Using star's light, we can approximate the temperature of the outer part of the star where this light is emitted. In the star spectrum, we also see absorption lines. Now, if you remember back to atomic physics, the absorption lines correspond to specific electron transitions in atoms. And every element has different electron transitions. So every element will have different absorption lines. So for example, hydrogen has an absorption line at 656.3 nanometers. If you see that absorption line in a star spectrum, there's hydrogen in that star. If you see an absorption line at 527.0 nanometers, that means there's iron. If you see an absorption line at 588.9 nanometers, there's sodium, and so on and so on. So using the absorption lines, we can figure out the composition of a star. Now let's take a look at the Hertzsprung-Russell diagram, or HR diagram. So this is a graph where we plot luminosity of the star on the vertical axis, and actually it's log of the luminosity on the vertical axis. And actually, we're not going to plot luminosity in watts. Instead, we're going to use solar luminosities, which is represented this way, L with a little circle and a dot next to it. That represents the luminosity of the sun. So on the vertical axis, I'm going to plot the luminosity of a star in multiples of the luminosity of the sun. Okay. On the horizontal axis, I'm going to plot temperature. However, I'm going to do it a little bit strangely. Temperature is going to increase to the left. That's odd, but there's a historical reason for it. So temperature increases to the left, and it's going to increase on a logarithmic scale. If we do this, and then we plot stars on this graph, what we find is that 90% of the stars that are visible are along a line right here. This line is called the main sequence. So again, 90% of the stars that we can observe are along the main sequence. Now, stars also show up in a couple other places. They show up over here, and they show up there, and then a very few stars show up in this little corner down here. Now, before we go any further, this temperature axis, we can also think about it as kind of a color axis, because the very, very hot stars, they're going to be emitting a lot of blue light and then less light of the other colors, just because of how a black body spectrum works. So the stars over here on this side are going to be bluish-whitish. And then if we go to slightly lower temperatures, we'll have whitish stars. And then if we go to slightly lower temperatures, we'll have yellowish stars like our sun. And then over here, we have orangish and then reddish stars. Now the stars in this group right here are called red giants. Stars in this group up here are called supergiants. And then the stars over here in this corner are called white dwarfs. And we're going to think about each of these. So the red giants, let's start there. The red giants, you can see they have temperatures that are cooler than the sun's. However, they have much higher luminosities than the sun. So if we look at the luminosity equation, luminosity is equal to sigma A T to the fourth. If they have a lower temperature, but they have a higher luminosity, that means that the surface area must be much larger than that of the sun. These are really big stars. They have big surface areas. They're physically large stars. That's why they're called giants. They're called red giants because they're the color red. The supergiants, if we look at them up here, they have enormous luminosities. And they're all colors, but they have really huge luminosities. In order to get those kinds of luminosities, they must be very, very large stars compared to the ones on the main sequence. So they're called supergiants. And then the ones in this corner, these white dwarfs, they're very, very hot. If you look at their temperatures, they're among the hottest kinds of stars, but they have very low luminosities. If you look at the luminosity equation, the only way that you could have a very high temperature but a very low luminosity is if you also have a low surface area. So these are very small stars. Okay. Now, on the main sequence, there's a relationship between the luminosity and the mass of the star, and it's this. Luminosity is proportional to the mass of the star to the 3.5 power. Now, this is an approximation, but it works pretty well. What I want you to notice about this is that it says that mass has a very large effect on the luminosity. So, for example, if we were to double the mass of a star, the effect that it would have on the luminosity of doubling the mass is the luminosity would be 2 to the 3.5 power times larger. In other words, it would be 11.3 times larger. So double the mass, 11.3 times greater luminosity. If we have 10 times the mass, then the luminosity will be 10 to the 3.5 times bigger. It will be 3,200 times bigger. So larger stars have much greater luminosities. If we think about this from a fuel perspective, so a star with twice the mass will use up its hydrogen at 11.3 times the rate, right? Because the luminosity is ultimately coming from fusion at the center of the star, from the core of the star. So more mass means you have a much greater luminosity. You're using up your fuel much faster. A star with 10 times the mass will use up its fuel at 3,200 times the rate of the other star. So higher mass stars, even though they have more mass and have more fuel, they will run out of fuel much faster. So for example, the very highest mass stars will burn through their fuel in a few million to 10 million years. The sun has been burning its fuel for 5 billion years, and it'll go on for another 5 billion years. So its fuel will last a total of 10 billion years. And then the lowest mass stars, well, they'll burn their fuel for about 500 billion years. Now let's take a look at stellar evolution. So the formation of stars, the lives of stars, and the deaths of stars. A star is formed when a part of a nebula begins to collapse, for whatever reason. When the nebula begins to collapse, the gravitational potential energy decreases as the gas cloud gets closer and closer to itself. If the potential energy, the gravitational potential energy of the gas cloud is decreasing, energy conservation tells us that the energy has to go somewhere. The energy becomes kinetic energy of the molecules of gas. In other words, if we have more kinetic energy in the molecules, the temperature increases. So as the gas cloud collapses, the center of the collapsing gas cloud becomes denser and hotter. And it becomes denser and hotter and denser and hotter until it becomes dense enough and hot enough that it can fuse hydrogen. Once the hydrogen begins to fuse, a star is born. All right. Once the star is born, it joins the main sequence. Stars burning hydrogen in their core are on the main sequence. Now, along that main sequence, luminosity depends on the mass of the stars, and the temperature depends on the mass of the star. So where you are along the main sequence on the HR diagram depends on the mass. Low mass stars are over here, high mass stars are over here. The main sequence is where a star spends most of its life. And that's why when we look up into the sky and we look at all the stars, most of the stars that we see are along the main sequence. Now, after the main sequence, interesting things start to happen. And multiple things can happen. So, whatever it is, stars fuse hydrogen in their core. But when they start to run out of hydrogen in their core, and there's not enough hydrogen to provide that outward force to keep hydrostatic equilibrium in place, well, then gravity begins to win. The core will shrink. And if the core shrinks, the temperature of the core increases. And in that situation, the temperature of the core increases, but there's no fusion or not enough fusion going on. The outer core also gets hot. And the outer core then becomes hot enough that it fuses hydrogen. When this happens, the outer part of the star expands and it cools. The star expands and cools. It cools, so it becomes redder, and it expands, physically larger. It becomes a red giant. Now, before we go any further, I want to look at a specific type of star that's in this situation called a Cepheid. So a Cepheid is a star where hydrogen is burning in a shell around the core. And it is an unstable star. It's unstable because of this. So the core compresses in a Cepheid variable star. And when it compresses, what happens is it becomes dense enough that radiation cannot escape from the region around the core. So if radiation cannot escape from the region around the core, well, can't escape, it stays there, the temperature of the core increases. So if the temperature of the core increases, there's going to be more fusion happening in the outer core here. And if there's more fusion, the pressure in the outer core is going to increase, and the core is going to expand. And the core expands, it's going to push the outer regions out. Okay, but then as it pushes outward and expands, then the core is going to become less dense, and the radiation inside of it is going to be able to escape, and so the temperature will decrease, there's going to be less fusion, the pressure is going to go down, so the core is going to compress. And then that repeats. A Cepheid variable star is a star that expands and contracts and expands and contracts, and that means its luminosity increases and decreases and increases and decreases. And it turns out Cepheids are important because there is an observed relationship between the period of oscillation and the luminosity of the star. So if we observe a Cepheid from Earth, and we can see the period of its increasing and decreasing brightness, then we can use that to determine the luminosity of the star. There is a relationship between the period and the luminosity of the star. It's called the period-luminosity relationship. So we observe the period. From that, we get the luminosity of the star. If we can get the brightness of the star just by looking at it, then we know the brightness and the luminosity of the star. And from this equation, B is equal to L over 4 pi d squared. If we know brightness and luminosity, we can get the distance to the star. Cepheids are ways to determine distances to the stars. Now back to stellar evolution. For stars with less than 4 times the mass of the sun, or 4 solar masses, represented this way, M with a little circle and a dot. These stars, after they've burned the hydrogen in their cores, they have an outer core that's fusing hydrogen to helium. And when enough helium builds up in the core, then the core is able to fuse helium into carbon. But these stars are not massive enough to reach the temperatures and pressures necessary to fuse carbon into anything heavier. Instead, what happens is the core of carbon shrinks and heats up, and it blows off the outer layers of the star. The outer layers physically leave the star, and once they're blown off, they turn into what's called a planetary nebula. Now, planetary nebulas don't have anything to do with planets. They're just called that. And then we get a leftover naked core of the star. Now, this core is no longer doing any fusion in it. It's not massive enough, and it doesn't have enough hydrogen or helium to fuel. It's just carbon, really. So the core shrinks, and it heats until it reaches an equilibrium. And the equilibrium is between the gravitational force inward and an outward force called electron degeneracy pressure. Now, this electron degeneracy pressure comes from quantum effects. It comes from when you try to push the electrons closer and closer together. Eventually, the electrons just won't have it anymore. The electrons push against each other, and this is a quantum effect. It's a very extreme state when you get to this point. The core is now very, very dense. It's about 1 billion kilograms per cubic meter, and it's at a very high temperature. So what that means is that you're left with a very tiny star with a very high temperature. It's called a white dwarf. On the HR diagram, it's right here in the lower left, because it's got a low luminosity because it's so physically small, and it's got a very high temperature, and so it's white in color. Now, these white dwarfs are about the size of the Earth, but they have 10% to 140% of the mass of the sun. Now, going back to the HR diagram, if we think about the evolution of a star with less than 4 solar masses, it starts out here on the main sequence. Once it burns up the hydrogen in its core, it becomes a red giant. So it moves over to this section of the HR diagram, and then eventually, when the core is not able to fuse anything anymore, the planetary nebula is blown off into space, and the star becomes a white dwarf and drifts over to this part of the HR diagram. Now, for stars with masses more than 4 times the mass of the sun, more than 4 solar masses, These stars are massive enough that the story is similar up until the point when you have carbon in the core. At that point, these stars are massive enough that the core pressure and temperature can fuse carbon. And it can fuse carbon into oxygen and then nitrogen, all the way up to heavier elements like nickel and iron. And if you remember back to nuclear physics, nickel and iron are the most stable elements. So the core becomes denser and hotter until nickel and iron fuse. But this doesn't release any more energy. Those elements are very, very stable. If you fuse them, you don't release any more energy. So what happens is the core collapses at this point. There's no more outward force that's producing energy. There's no more fusion to create an outward force, so gravity wins. The core collapses, and the core is too massive in this situation for electron degeneracy to even support it, like it does in a white dwarf. Now, when the electron degeneracy is not able to support the star, that occurs when the core mass is over 1.4 solar masses. Now, 1.4 solar masses is called the Chandrasekhar limit. Above this mass, electron degeneracy cannot support the star. And what happens is the protons and the electrons in the entire star combine. You get this reaction. Proton plus electron results in a neutron plus a neutrino. So this happens very suddenly. And when this happens, the protons and the electrons go away, and they all turn into neutrons and neutrinos. And if you remember neutrinos can pass through normal matter very easily. So when this occurs, the neutrinos just escape. And all you're left with is a big core made of neutrons. Neutrons don't have an electrostatic repulsion. They don't have a Coulomb repulsion. So they can be very, very close together. They can be very, very dense. Essentially, the core of the star achieves densities like densities inside of a nucleus. You get the core of the star is completely made out of neutrons at the density of a nucleus. The core shrinks to about the size of a city, about 10 kilometers across. Now, meanwhile, this core has, shrunk to the size of a city. The outer layers of the star fall into this empty space now. They fall in towards the center. When that happens, they get very, very hot because they're all compressing, and the star, or the outer part of the star, bounces off of the core. This is a supernova. The outer part of the star explodes in a huge burst of luminosity. And when I say huge, it releases luminosities billions of times more than the sun. Now, the core here, the leftover core, is supported by what's called neutron degeneracy. And that's a quantum effect. It's kind of similar to electron degeneracy, except it's much stronger. And as long as the core's mass is below a certain limit, we get what's called a neutron star. And a neutron star is a star where the inward force of gravity is supported by neutron degeneracy. Now, these are stars that are, a couple solar masses and about the size of a city. So very, very dense. Now, if the neutron star is above the Oppenheimer-Volkoff limit, and the Oppenheimer-Volkoff limit is not well pegged down, but it's approximately 1.5 to 3 solar masses. If the core is above that limit, even neutron degeneracy isn't strong enough to provide the outward force necessary. And in this situation, gravity wins. Ultimately, there is no force that's able to support the star. Gravity causes the star to shrink down to essentially no size, and we get a black hole. What this looks like on an HR diagram is we have a massive star over here, and once it is able to, or once it runs out of fuel in its core, it goes over here to the supergiant branch, and once it's in the supergiant branch, eventually it undergoes a supernova and leaves the HR diagram completely.